We're looking at the empty loaded state of the 666 pancake system on turn on of this state, and we can see we got 1 amp in the middle serving 0.33, 0.34, phases 1, 2, and that's a contradiction. And we can see that all the amperages are hovering around 1/3 of an amp. This is without a load on the basic conditions of the circuit that we're drawing on for tests without energizing the field. Phase 1 has practically no voltage rise. 0.8 only becomes 1 volt internally. Phase 2 has appreciable voltage rise. 0.9 volts becomes 8.6 volts internally. And on phase 3, 0.7 volts becomes 10.2 volts internally. And on the comparisons, what we're interested in is that figure right there. Between 2 and 3, we have 18 volts. That tells us the voltage output from Q voltage rise of the totality of the system, whereby we have combined 3 phases into 1 phase of action. Now, the way we have combined those 3 phases into 1 phase of action is to construct secondaries, and we have a white chip, a blue chip, and a red chip, noting the positions of those 3 secondaries around the system. And we also now have, of course, the scoping of the voltage derived from that secondary system. And we want to again look at the open loaded state so we can later compare it to the loaded state in various forms. We all have 1/3 of an amp on the phases. Now, what seems to be happening here is that phase 3 is now going to be acting as the predominant current drop phase, I guess you could call it that. We also have a capacity attached that can be attached to those secondaries, and when in fact we do add a capacity to those secondaries, we now have amperage circulation in those secondaries between the coils and the capacitors, and therefore the load now, the source now sees a load, and those 0.3 amp figures will change according to the load. Now then, what we want to see here is the response of that voltage upon addition of 19 microfarads to the system, which incidentally, that is a high estimation of the needed capacity for 3 of these 2.3 millihenry coils in series at 465 hertz. But we find that capacities added on circuits have a very broadband response. And what we'll do now is simply go in there and attach the capacity and show the secondary amperage consumption and the change of the primary amplets. You should have been able to see that the voltage went up in this case, and we now find we have 208 milliamps of circulation derived from them 3 coils hooked in series. And we have our new change circumstance, whereby seemingly only phase 3's amperage dropped 0.16 from a former 0.33 value, and phases 1 and 2 are practically the same. Most notably, I don't know if we began, when we showed an 18 volt total Q factor, because we've taken out this load now, that Q factor has been reduced to 10.2 volts. Now what we're going to do, we got a ferromagnetic transformer over there. That box thing, we got a voltage meter on its outputs. We're going to hook that 41 step-up transformer up to our air core process. And while we do that, we want to, of course, note any kind of input drop of that voltage. So we're going to try to get back to our scope in there. And we're going to go over there and input primary. And you should be able to see that when we added the reactance of that primary to the source, there was practically no drop. And now over here, we're obtaining 146.8 volts through the air. I've seen it go higher than that. And then to end this video here, show our new operating circumstances. We have 0.8 volts on phase 1, no voltage rise. Phase 2, we have 1 volt. Phase 2, we have 1 volt, enabling 8.2 volts, voltage rise. Phase 3, we have 0.9 volts, enabling 5.8 volts, and then 10.9 volts between them. And on our amperages, phase 1 and 2 barely changed, phase 3 went down, and that should be the end of it.